Hi, in the part 1 of Contour Detection 101, we learned what contours are, how to detect them, how to pre-process them, and do some other interesting things with them. If you haven't watched that video already, then the link for that would be in the description below. Now, detecting contours alone won't just cut it. If you want to build contour-based applications, you need to do things like extract the largest contour, or sort contours regarding to size, or draw a hull around them and do some other sort of manipulations with contours. In this video, we'll learn exactly those things. We'll learn how to manipulate contours to do and perform various tasks. So let's get started. For today's tutorial, we'll be using this Jupyter notebook. You can download it using the link in the description below. As always, at GDI, instead of coding via script, I use high-end Jupyter notebooks so you can revise all the things you learned in this video at your own time. All right, let's start. So the first thing that you need to do is import all the libraries that you're going to use. So I'm doing that with this cell. Then what you're going to do is read the image that you're going to work on. So I'm reading this image, and then I'm using Matplotlib to display that image. All right. So this is the image which we will be working on today. And if you haven't noticed, this is the same image that we used in the previous tutorial, Contour Detection 101 Part 1. All right. So after we have read the image, so the next thing that we are going to do is detect and draw contours from this image, right? And we have already covered how to do exactly those things in the previous tutorial, but just for the sake of revision, I'm going to briefly cover how each line works here, right? So the first thing that we do here is read the image in grayscale mode. Since this image is already pre-processed, as you can see, it's in already binary format. So I don't need to, do some thresholding or canny edge detection because the image is already pre-processed, right? All right. After reading the image in grayscale, we're gonna run this function called cv.findContours, which is used to detect contours. We pass in the image. We specify the retrieving method. We're using connected components. You can use retrieve list or retrieve external. It would work fine for you. And then we're passing the approximation code here. And then finally, we're using CV to draw contours to draw the contours. You pass in the image, you pass in the detected contours that you detect here. And then you specify how you want to draw the contours. -1 tells the tells the method that you want to draw all the detected contours, and then you specify the color. 0 to 550 means we're gonna draw it with the green color, BGR, right, and the thickness of the line. And like I said, this is the hierarchy in the previous tutorial, which I briefly touched upon, and we're not gonna be using this returned variable. All right. So to detect contours, you first need to pre-process image. Then you pass the pre-processed image in the find contours function, and then you get the contours back, and then you use the draw contours function to draw the contours. So that's how the whole contour detection in essence works. All right, after we have drawn out the contours, we will use plt.imshow to display using Matplotlib. All right. And as I covered in the previous tutorial, we're going to be reversing the image channels because Matplotlib displays it in RGB and we want the OpenCV reads it in BGR. So that's the reason we reverse the channels by using this snippet of code, colon, and then colon, -1. All right, let's just run this. So as you can see, all the contours are drawn out by using this green line. And you can see all the contours here, right? So this contour, this, and all these contours are drawn out. All right, now let's get to business. All these things that I've just, explained here, I already covered it in the previous tutorial. Now let's get to the interesting bit. How about we start with extracting the biggest contour in this image? What do you think is the biggest object or the biggest contour in this image? Think for a moment. If you think this object is the biggest contour, then you're right. Now let's see this in code. All right. So the first thing I'm going to do is again read the image in grayscale, detect the contours, and to detect the biggest contour, I just need a single line of code, and that is this is the line which I'm going to be using to extract the largest or the biggest contour present inside the image. And all I'm going to use the Python's max function. And then I'm going to pass in the contours here, and then I'm going to specify the criteria to which the max function would consider when extracting the maximum contour. So I'm specifying the criteria as the contour's area. CV2.contour's area gives the area of contour, right? So if I do something like, like this, let me just pass in. Let me just first run this code. All right. As you can see, what it does, max function goes over all the contours, and then by using this contour area criteria, it extracts out the biggest contour. And then I have stored the biggest contour in this biggest contour variable, and then draw out just this contour using the draw contours function. So this is how you can extract biggest or the largest contour in an image, right? And this is a really, really useful technique. And before I explain the usefulness of extracting the largest contour, just let me show you what CV2.contour area gives you. All right. So if I use CV2.contour and right contour area, and I passed in the big, maybe the biggest, it will return to me, I think, is it that biggest contour? All right. So if I run this up, yeah. So as you can see, this function returns to you the area of the contour. So by specifying this criteria, you can sort the image or get the maximum of a contour, like using any other criteria. But the most common criteria is, like the area of the contour when extracting the largest contour in an image. All right. So this is how this contour area works. Now, let me explain to you the importance of extracting the largest contour in an image. So take a look at, like this example. So this is a beautiful teddy bear that I, drew, and this is some noise that I've added in the image. Now, when doing image pre-processing, you often do something called morphological operations, which is erosions and dilations, which, gets rid of this noise. But over times, even if you have, gotten rid of the noise, there's still some noise present, and which causes problems. So what you end up do is you detect all the contours, including the noise, and then you extract the largest object. So if if this was an image and I just wanted to, extract this teddy bear, just wanted to detect this contour. So if I do pre-process this image and do contour detection, then all these things will be detected as individual contours. But the only thing I'm interested in is the teddy bear. So how would I, extract only this bear? I would, do things like extract the biggest contour. And this is how I'm going to get this bear and ignore all the other things. And this is a really useful technique. Like I said, with morphological operations, you can get rid of the noise. But if suppose besides the teddy bear, some other object is present in the image and it's not noise, it's a little bit bigger, and you can't get rid of that thing by using erosions and dilations. This is when you use this criteria. Give me the biggest and largest contour in that image, and this is how you extract your target object that you're trying to detect. And this is when this technique is really useful. All right, now let's move on. Suppose instead of extracting the largest contour, you wanted to find the 3 or the 4 or any nth large contours. So in my case, for this image, I want to know what are the 3 largest or the 3 biggest contours present in this image. So in that scenario, I'm not going to use the max function. I'm going to use something called the sort function. So this is how this works. I'm going to convert the image in grayscale again, do contour detection again. And then instead of using the max function, I'm going to use the sorted function in Python. I'm going to pass in all the contours, and then I'm going to specify the criteria of the sorting as contour area. Again, I'm passing the criteria as contour area because I want to sort all the contours using the criteria as the area. So the the largest area, all the contours on the that have the biggest area are sorted in ascending or descending order. Now by default is ascending order, and I specify reverse equals to true, which sorts the contours in the descending order. So the biggest contour would be first, and the second biggest contour would be second, and the third biggest contour would be the third. And this is how the whole list would be sorted by using this sort function. All right. Once I've sorted all the contours, I just need to iterate through this list. All right. So what I do is you iterate through the first 3 contours, because I'm just interested in drawing the 3 largest contours. If I wanted to draw 4 largest contours, I would just replace these 3 with a 4, right? And then I'm drawing the contours, all these 3 contours, and then I'm also putting the text up there and specifying the number or the order of that contour in that list. So that is why I'm using the enumerate function, because I'm also interested in the index of that contour. Is it the first biggest? Is it the second biggest? Is it the third biggest? I want to know. So this is why I'm doing that. And then I'm gonna use Matplotlib to draw the contours. All right. So this is how this looks like. As you can see, this is the first biggest, and this is the second biggest contour, and this is the third biggest contour. So this is again a pretty useful technique. All right, let's move on to some other things. Now, once you detect contours, now as you can see, all the contours are are the outline of the exact image. But there are cases instead. For example, when you're doing object detection, you don't want to segment out the objects. You just want to draw a bounding box around the contour. So how can you do that? So in OpenCV, you have two techniques to do exactly that, to draw a bounding box around a contour. And this is really useful. By using these techniques, you can have an object detection pipeline that doesn't even involve machine learning or deep learning. You can have a classical vision outline pipeline in which you detect contours and you use you draw a bounding box around them. In essence, you're doing object detection, but without machine learning or deep learning. And this have a variety of use cases. You don't need any data to train on, and the whole system is really compute light and many other benefits. All right, the first and the most common technique that you'll be using to draw a bounding box around the object is by using this function called cv2.boundingRect, and you pass in the array, which is the contour. For example, whenever you're detecting contours, each contour itself is a list or an array. And then what you do here is passing, let me just show you the code here. You read the image in grayscale as always, you detect the contours, and then what you do here is you use this function called cv2.boundingRect. You pass in the contour. So I'm specifying the second contour. So for example, if I have done 0 here, then it would have drawn the first contour. But if I pass in 1, it would have considered second contour. And the thing is that you need to pass in this function only a single contour, not the list of all the contours, right? So you need to select the contours first. You can, right now I'm just randomly passing in a single contour, but you can use some criteria, like you can use the maximum function and grab the biggest contour and then draw the bounding box around only that contour, right? So I can use something like I can use the max function to grab this biggest contour, and then I can just pass in this contour instead of doing contours 1, right? So this is your own choice. Ideally, how this works is that you specify some criteria and grab your target contour, and then you draw a bounding box around that contour. All right, let's move on. So by using cv2.boundingRect and by passing in a specific contour, you get back x, y, and wh. So this is the x1, y1, and this is the width and the height of that contour. And by using these 4 variables, we know that you can use these 4 variables and pass it to the cv2.rectangle function, and it would draw a bounding box around that object, right? So let's just run this code. So as you can see, by passing it this contour, it has drawn a bounding box around that. Let me just change this contour a bit. So now it's drawing a contour around this object. So you can switch around and play around with this, and you can draw bounding box around various other contours. Now notice there is a problem here. The problem is that this bounding box is pretty big, and it's in fact covering another contour, this triangle. And it shouldn't do that, right? So if in case you just wanted to grab a single contour and don't want the bounding box to overlay with another contour, you need to use another bounding technique. So this is what we're going to cover next. So this is a rotated rectangle technique. In this technique, you use this function called cv2.minAreaRect, and this gives you a bounding box, but that bounding box is a special kind of box which covers the minimum possible area that it needs to cover. Not like this bounding box where it draws a full box, and the rest of the things are also overlapping with this box. So if this is an issue, then you should be using this function. But there are a few issues with that function. The common issue would be that you can actually crop this part out, because when you're cropping parts out of an image, you need a squared area. But if you're not drawing out a squared area, then you can't just crop out an image. I'll explain this in a bit, but right now let's just run this code. To draw a rotated rectangle, which is what this function does, is what you need to do is, instead of using bounding rect, you just use this function and pass in the contours, and you get an object. And I'll explain what this object gives you. It's essentially a tuple. And let me just first run this code. So the first thing that you do is you convert the image to grayscale, you detect all the contours, and then instead of using the bounding rect, you use this function cv.min_area_rect. You pass in a targeted contour, you get a rect object. And but then what you do is use another function called cv.boxPoints and pass in this rect object, and then also convert this object into integer, because by default it's going to be float and you don't want float values. And then what you do is, after getting this box object, you draw the contours. You use cv.draw contours, and then you pass in this box inside a square bracket. So it's a list of contours, and then you specify 0 because there is only one object present in this list which you just created, and then you display the image here. All right, let's run this code. As you can see, this is min area rect. So this is how a min area rect works, and this is how the result looks like. And as you can tell here, it's only taking up the minimum available area to enclose the whole contour, and it's not overlapping with any other object. And now I'm gonna tell you the drawback of this technique. So you can't crop out this particular segment because it's not a squared area, it's a rectangle. It's an area like this, and this is the same reason I'm not able to use the cv.rectangle function to draw this box. Because if you look at this box points, let me just display this box for you. So if I draw out this, you're gonna get a series of points like this, 4 points. So like this would be 1 here, 2nd here, 3 here, 4 here. It's not a squared area, and because since it's not a squared area, you're not gonna be able to draw. You can't just draw out a rectangle with this one. It's a rectangle. It's called a rotated rectangle, but it's not something that you can crop out of the image. So in when you're doing object detection, most of the time that you're going to be using this function, but in some specific circumstances you would be using this function. And this is actually a polygon. And when you want to draw a rectangle that's returned via min area rect, you have two options. Either you can use draw counter functions, or either you can use cv.polygon function to draw this out. So because it's a list of 4 points, not 2 points to draw a rectangle, you need to either draw a polygon or you need to draw using cv.draw contours. All right, now let's look at the data format returned here. So by using min area rectangle, it gives us a rectangle, an x1, y1, and with an height just like this function returns, but it also returns a fifth variable. So min area rect also gives you these variables, but it also gives you a fifth variable, and that variable is the angle of rotation of the rectangle. And this is the angle that you need to rotate the rectangle to best fit that contour. So let me show you exactly how this looks like. So see, I have printed the rect object out, and as you can see, we have an xy tuple here, and then width and height here, and then we have this angle, so 53.3, this angle. And then what this box point function does, it takes in a tuple which contains an x1, y1, and with the height point and also an angle, and then it uses that angle to rotate the rectangle and gives you the new points. And these are the new points that the box array contains. Again, to reiterate, min area rect gives you a tuple that contains x1, y1 with height and an angle of rotation to best fit the rectangle, and then you pass this object in the box points function, and which this box point function returns you the new points that are now aligned with that rotated rectangle, x1, y1 and x2, y2 points. Sorry, they are exactly 4 points, or how many points, whatever points that it needs to cover. So this is 1 point, this is 2 points, this is 3 and 4. These are exactly 4 points that this box is returning to enclose that contour. All right, so that is how these two enclosing functions work. All right. All right, let me just compare to you how much like area this is saving when we compare these two enclosures. As you can see, this is taking up a lot less area. That's why it's called min area rect, right? So this saves you a lot of area in case you don't want to overlap. This is the function you will be using. All right, now let's take a look at the final enclosing technique. This is called convex hull, and to use that you will be using cv2.convexhull function. You pass in the contour points and then it returns to you a hull. And what exactly is a hull? I don't want to describe it to you because I first want to show you, and then I'm going to go over the code, and then we're going to discuss what a hull is and what are its actual use cases. All right, so let me just first run this code. So this is what a hull looks like. All right, so as you can see here, this is what a hull is. And let me just minimize this. I didn't even do that, and run this. So this is what a convex hull is. And so we have this image. This is how the normal contours are drawn in this image when you do all the pre-processing correctly. And this is what a hull looks like. Instead of drawing outline or an exact line, your point by point outline of the whole contour, it's an approximation of how the whole contour is. So by definition of convex hull, so you can consider a hull that looks for convexity defects and corrects it. So convexity defects are something like this. So areas in the contour that are bulged in. So look at these corners. These are bulged in. So this is what we call a convexity defect. It's actually a concave curve, but we call it a convexity defect. If it was bulged out like this part, this is called a convex curve, right? But if it's bulged in like here, the corners of this, it's called a convexity defect. And a hull bypasses or corrects convexity defects, and it doesn't go over the defect. So this is what an output result of a hull looks like. Let me show you an example of how this thing would be useful. So consider something like this. So suppose if you had an image like this, in which if you have detected contours, then what you would have gotten is something like this. And suppose if the whole the thing that you wanted to detect was this this tree and the apples. Since the apples are not connected with the tree, it's spread out and it's disconnected. You won't be able to extract these apples out with this particular contour. So there are cases when the main contour has parts of it that are spread out, that are spaced out, and that are not exactly connected. And then but you want the whole package. You want this whole contour along with the apples and all of. So there are a lot of real world cases in which you would find things like that. And one of the common common things that come up are the main contour is broken down into have sub parts, and you need those sub parts. And this is where convex hull would be useful. If I had extracted this contour using a contour, I would have missed out the apples. But if I had using a hull technique to extract this contour, I would have also gotten the apples here. Right? So this is how this hull is useful. Let me show you another example and a really useful case of convex hull that I used. So take a look at this application that I built a few years ago. And in this application, what I essentially did, it's a really interesting application. I use background subtraction to get this mask, and then pre-processed it using morphological operations, and then drawed a hull around that hand, and then used shape detection. So to figure out what exactly, am I holding a 5, am I holding a 4, am I holding a 3? So this is what I'm drawing a hull. When I drew a hull around the hand, it essentially became a shape. And when it became a shape, I can do shape analysis to find out if I'm making a required targeted shape in order to trigger some actions. So this way, I actually created a something like a hand gesture recognition calculator without using machine learning or deep learning. And it was really interesting. So without using any machine learning or deep learning, you created something like this, right? So this is how useful this hull feature is in contours, right? So you can do a lot of cool things when you figure out how to manipulate contours. And like I said, I've created a number of interesting applications just around contours. So let me just go over the code, I guess, because I didn't cover it. So what you need to do is first read the image, And then we are making some copies. I'm converting to a grayscale, and then because since this image is not pre-processed, I need to convert this image, do some thresholding in this image in order to get a black and white binary image. As we covered, I've already pre-processed this image example in the last video. So if you're not clear on how why I'm doing the thresholding and the grayscale conversion, you need to watch that video. Like I said, the link for that would be in the description. All right, so after I've gotten a thresholded image, what I'm going to do is now find out contours, and then I'm going to extract the first available contour in order to, because this image would be, only consist of a single contour, and then I'm going to extract the first available contour. In case you're getting some issues, for example, sometimes when an image contains a single contour, sometimes 2 or 3 contours are detected, and the reason for that is there's noise that you can't visually see, but it's present there and it's being detected as a contour. When that happens, what you can do to avoid that is detect only the maximum contour. You can use the max functionality and then grab the maximum contour and do rest of the pre-processing with that contour. All right, right now I'm just going to extract the first available contour and store it in the CNT variable. And once I've gotten the contour, I'm going to use a cv2.convex hull function, passing the contour, and I'm going to get this hull. And once I've gotten the hull, it's essentially a polygon around the whole object. You can draw it using a draw contours function. You pass in the hull, and then you display it. So this is how this whole thing is working. Now let me just briefly cover this variable. So there are two other variables. One is clockwise, which is not that interesting. The other one is return points, which it might be useful sometimes. But right now I'm just gonna tell you what return points exactly is. By default, this Boolean variable is true, and when it's true, what you're gonna get is hull points. So for example, let me just draw this out. So what hull essentially gives you is something like this. So these are x23, maybe something y23. So these are some specific points in the whole list of contours, and maybe this would be 27. So 27, y27, right? So these are, for example, to draw this tree out, they are, it might have given you this point, then it would have given this point, then it would have given you this point, then this point, then this point, and so on. So it's not giving you all the points in the contour, it's only giving you some specific points that you need to connect together in order to create a hull around the contour. So it's giving you some specific points, and this is what it gives you when the return true, the return object, the return variable here, the return points variable is true, which is by default. But if it's false, what it gives you the index of those hull points in the list of contours. And by the way, if you're not understanding this, then you don't need to get this for now, because without even understanding this particular small concept, you can use hull effectively. All right. So the thing it gives you when the return points variable is false is something like this. So if consider this the list of original contours. So when the contours are detected, what you're gonna get is a list of points of the whole contour. And then when I'm gonna extract the single zero contour, I'm gonna get a single CNT contour, which is gonna be a list of an array which is gonna contain a series of XY tuples. And there might be 100 points or 50 points, whatever the points are necessary in order to draw out an exact outline. So this is 1 point, 2, 3, 4, 5, 6. I mean, to draw an outline around this tree, there might be a couple of 100 points, that the CNT list contains, right? So what hull does, if return points variable is false, is that it gives you, if this is the contour list containing an XY tuple, X, this might be, this is X1, Y1, X2, Y2, then X3, Y3, things like that. And then so on, it goes on to the XN, YN. And what hull gives you, it tells you, take this point, one, this is the second point that you need to take, you need to skip this point, then you need to skip this, and maybe, pick this point up. And it gives you the index of the actual contour points that you need to use in order to create a hull around the main contour object. So this is what it gives you. This would be useful in a specific circumstance, which I'm not going to cover in this lecture. I'm going to make a series of 3 videos that covers what contours are, and I'm not going to cover each and everything. There are a lot of things that I'm going to skip in these 3 videos. This is the second video, and there's a third video coming up, which is going to be about contour analysis. And that would be a really exciting video. And all these 3 videos are actually a part of a course that I'm planning to publish very soon on my site Bleed AI. And this would be a single day course that would not only teach you how the whole all the nitty-gritty details regarding contours and a lot of other stuff, but it would make you able to create computer vision applications in a single day. And so that is why I'm creating a whole course around contours. And this is it is a mini course, and it's a single day course, and it's coming up in a few weeks. So stay tuned for that and for the upcoming video on contour analysis. And if you enjoyed this video, please make sure to subscribe to this channel and share it with your colleagues. See you in the next video.